This is part 4 of section 3.5 from Math 311, a course in linear algebra at Western Illinois University. So this is the fourth and final video for a series of lectures in this very important section, 3.5, on subspace, basis, rank, and dimension. We've done quite a bit, and right now we're going to culminate this section with a new version of the fundamental theorem of invertible matrices. We had the first version earlier in this course, and let me just show you that the first version says that if A is an n by n matrix, that means it's a square matrix, then the following statements are equivalent. A is invertible, AX equals B has the unique solution for every column vector B in Rn. C says AX equals 0 has only the trivial solution, that is x equals 0. D says the reduced row echelon form of A is the identity matrix, and E says A is the product of elementary matrices. So version 1 said that these first 5 statements are equivalent. That means if one of them is true, then all of them are true. Now we are going to add quite a bit more properties to this list. You'll see that these involve rank, nullity, involve the column spaces and row spaces, and it seems like quite a bit, but we're going to try to outline the proof of this using diagrams, okay, and try to make it accessible. You'll notice that I didn't make a special set of notes ahead of time for this, so I want to take notes as you follow along. All right, so we're going to let A be an n by n matrix. Okay, and we are going to start with the statement that the rank of A is equal to n. Okay. All right. Now remember, the rank, of course, is the number of non-zero rows of A in its reduced row echelon form. But we also said that last time that the rank is equal to the dimension of the row space and the column space. So if one of them is equal to n, then they're all equal to n. And remember, the dimension of a subspace is just the number of vectors in any basis it might have. Okay. Now, we said that the rank, if the rank is n, then the rank and the nullity has to equal the number of columns in the matrix. Okay, that's the case. That's from the rank theorem. So this is equivalent to saying that if the rank of A is equal to n, then the nullity of A has to be 0. Okay, and that's from the rank theorem. Okay, and remember, the nullity is the dimension of the null space, and the null space is the set of all vectors x such that A times x is equal to 0. So if the dimension of that subspace is 0, then that subspace only has the 0 vector as an element. Okay, so this is equivalent to saying that AX equals 0 has only the trivial solution. Okay, well, we know that this statement from version 1 is equivalent to 4 other statements. Namely, that AX equals B has a unique solution for any B. We also know that if it says A is invertible, it implies A is invertible. Also implies that the reduced row echelon form of A is equal to the identity matrix, and A is the product of elementary matrices. So we know from version 1 that all of these are equivalent. Okay, this is version 1. Fundamental theorem of invertible matrices. That's what that stands for. Okay. So right now we have 9 statements that are all equivalent. Okay. Now I want to add some more. We know that the reduced row echelon form tells us gives us a basis for the row space, and if the rows of the identity are just, well, they form a standard basis for Rn, right? So everything in Rn, if you take it as a row vector, it's going to be a linear combination of the rows of In, which means it will be a linear combination of the rows of A, since they generate the same space. So this implies that the row space of A is equal to Rn. Right, that this implies this. Okay. All right. But of course, this implies if the dimension of Rn is just n, so the dimension of the row space of A is just going to be n. So this implies that. Right. So those are equivalent. Now we also know that if Ax equals 0 has only the trivial solution, that means there can't be any non-trivial linear combination of the columns of A equaling 0, right? Because the product Ax represents a linear combination of the columns of A. So that means the columns of A have to be linearly independent. Well, if they are linearly independent, we already know the columns of A, by definition, span the column space of A. So that means the columns of A are a basis of the column space of A. Okay. We already knew they were a spanning set, but now that they're linearly independent, that means they form a basis. And of course, because we have n columns, that means the dimension of the column space is n. Okay. So, all right, so these are all equivalent. All right, now to proceed further, to prove the other stuff, we need to make an observation here. And that asks, do we have to bring the transpose of A into this discussion? Okay. So, and the first thing is we have a very important, we'll call the theorem. And that says the rank of A transpose is equal to the rank of A. A reason for that is because the rank of A is equal to the dimension of the row space of A transpose. Okay. Well, this will all remember the rows of A transpose are the columns of A, so this is equal to the dimension of the column space of A, which is equal to the rank of A, right? So that's the proof of that. I think what we also want to observe is that the column space of A transpose is equal to the row space of A. Obviously, the columns of A transpose are the rows of A, and the rows of A transpose are the columns of A. Okay, so keep that in mind as we prove this. All right, so to prove this, to prove the rest of this, we're going to use the following. Okay, so we obviously we know that the rank, if the rank of A is equal to n, that happens if and only if the rank of A transpose is equal to n. Okay, they're equal. Okay, and that, of course, is equivalent to the version 1. That is, this version 1 of the fundamental theorem for A transpose. Okay, where by that I mean it's the same set of statements where A is replaced with A transpose. And if this holds, so basically all of these properties will hold if A is replaced with A transpose. Okay. So with this version 1, we get a couple of things. With this version 1, we first get that the column space of A has to be Rn. Okay, the reason for that is, that version 1 implies that the row space of A transpose has to be Rn, but the row space of if the row space of A transpose is just the column space of A. Okay. And then, this will imply that the dimension of the column space of A is going to be n. And then that goes, but that then automatically implies that the rank of A is equal to n. Okay, so we have all these are now equivalent. All of these statements, we can ignore these. We sort of just use these are intermediate steps. So all of these are equivalent. And then we also know the version 1 for A transpose also says that the rows of A must be linearly independent. Okay, now why is that? Because, when we use this for replace A with A transpose in version 1, that gives us the columns of A transpose are linearly independent, but the columns of A transpose are just the rows of A. So the rows of A are linearly independent. And then that implies that the rows of A are a basis for the row space of A. By the same reasoning, they're already span the row space and they're linearly independent, so they're a basis. And that implies that the dimension of the row space of A is equal to n. And then that goes back to implying that the rank of A is equal to n. Okay. All right. So now that we've implied, we basically proved everything now. The only other tidbit we should notice is that if we know that if the column space of A is Rn, and the columns of A are a basis of the column space of A, then of course this is the same. These two statements together say that the columns of A are a basis of Rn. Okay. Okay. So then, and the same thing happens if the row space of A is Rn, and the rows of A form a basis of the row space of A. Then the rows of A will be a basis of Rn, and then that finally proves this wonderful theorem, or the next version of this theorem, all of this here. So that includes all of these statements, and hopefully you were able to follow this okay. If not, you can replay the video again But it's a very, very important theorem, and believe it or not, we're going to add even more properties to this version. Okay, so you can tell a lot about a matrix if it's invertible. Okay, then the one last thing I wanted to talk about was the uniqueness of representation with a basis. So, so here's another little theorem. Okay, so if V1 through Vn is a basis of a subspace S, and A1 V1 plus dot 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 plus AN Vn is equal to B1 V1 plus dot 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 plus Bn Vn. Then A1 equals B1, A2 equals B2, and so on to AN equals Bn. Okay. So the scalars used in this, there's only one. Once you fix a basis, there's only one linear combination. There's only one way to represent a vector in that subspace with regards to, in terms of that particular basis. And the reason why is this, or the proof, say why. Okay, well, we can do, if this equals this, we can subtract this whole linear combination from both sides, so we get A1 V1 dot 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 plus AN Vn minus B1 V1 plus dot 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 plus Bn Vn equals 0. And then we can distribute this minus sign and group the V1 vectors together, so this will be A1 minus B1 V1 plus A2 minus B2 V2 dot 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 plus AN minus BN Vn equals 0. Okay, the A2s and the B2s are somewhere in these dot dot dots. Okay. Okay, so then, because since the V's are linearly independent, since the VI's are linearly independent, and they're linearly independent because they are a basis, we have A1 minus B1 equals 0, A2 minus B2 equals 0, and so on. AN minus BN equals 0. That means that A1 equals B1, A2 equals B2, and so on. Okay. So that's why the unique. They're and then these and so if W is in S and W is represented by this linear combination, then A1 through AN, these are called the coordinates of V with respect to the basis V1 through Vn. Okay. And they're unique with respect to the basis. So obviously a different basis will give different coordinates. For example, if we take in R2, if we take the vector 7, 3, obviously we can write this as 7 times 1, 0 plus 3 times 0, 1. Okay. Okay, because 1, 0, 0, 1, that's the standard basis for R2. But we can also write 7, 3 as 10, I think that'll be 5, 1, 1, plus 2, 1, negative 1. Okay, and remember, 1, 1 and 1, negative 1 were also also a basis of R2. Okay, so we can say 7, 3 are the coordinates of 7, 3 with respect to this basis, but 5, 2 are the coordinates of 7, 3 with respect to this basis, 1, 1 and 1, negative 1. Okay. All right. So those are the coordinates. There's a couple other things that you can read in this chapter. I think you can basically look at the proofs and treat them as exercises. But I think we've covered a lot of material now. So now all I can say is go work on the exercise, practice, 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 and we will see you next time.